I wasn't careful enough in making up the function here. I didn't really check it out. I just made up a function without thinking too hard, and assumed that if we integrated it around a closed a unit circle, we'd get something besides 0. That isn't the case, but that's okay, because we can easily modify this to something that does give us not 0. So let's look at the example. Okay, here's our function, f of x, y, and we define our path by xi plus yj, where x equals cosine t, y equals sine t. Now, I could have, and probably should have, where is my, we'll use this one. I could have said my path is a vector r of t, where r of t is xi plus yj, with x equal to cosine t, y equal to sine t, and t from 0 to 2 pi. And that might bring this into a little more familiar perspective. Now what we want to do, the first thing I ask you to do is, well, I didn't ask you to do it, okay? The first thing we want to do when we see a function of this nature, this is a vector function. Now let me digress for a minute and give you another example of a vector function. The vector function gradient of x squared y squared, which is very easily calculated. I hope you know what gradient means because you have a test over that currently. So here's the gradient of this thing. Okay, so here's a vector function. Some function of I, some function times some function multiplied by I, another function multiplied by j. These functions have the property that they come as the gradient of some other function. This function doesn't. That can be argued easily enough. We'll see that. I did say a little bit about that in the class, basically because if this is a gradient of some function, then that function has to have a y component, and if it has a y along with an x, and if it has a y component combined with an x, so does this one, and so this isn't a gradient. And I think I'm right about that. I haven't worked that out. I have to write it out carefully to be confident. Okay. Anyhow, this path clearly gives you a unit circle of radius 1 about the origin. As t goes from 0 to 2 pi, you go around this circle in the counterclockwise direction. I've plotted purple vectors around this circle. They're purple vectors you can think of that describe this function at every point of space. So we could set a grid of points and draw the purple vectors and get a picture of this vector function. You'll see that in your textbook. I've confined my efforts only to the circle. When y equals 0, which occurs on the x-axis, the vector function is just x squared times I. Now there are only 2 points on the x-axis, this one and this one. At this point x is 1, at this point x is negative 1. In both cases x squared is 1. So at both of these points, your f of xy vector is just the vector 1, 0. I plus 0, just I. Okay? On the y-axis, x is 0 everywhere on the y-axis. So at any point on the y-axis, this component is 0. The coefficient of j is 0, and so is the coefficient of I. So you have 0 vector here and here. And I didn't indicate that. I could maybe indicate that just by putting a little purple dot here indicating, yeah, you've got a vector, but it has length 0. Now at the point, let's say, where t equals pi over 4, that would correspond to this point here along the 45-degree line on the circle. The sine is square root of 2 over 2. The cosine is square root of 2 over 2. Now, I'd also comment in class, if you have to use computer algebra software to figure these things out, or if you have to go to your calculator to figure these simple things out that I'm talking about here, you really need to wean yourself. Obviously, if you have a complicated function, there are functions that go beyond my ability to think through their behavior, their functions go beyond yours. And we don't want to try to do this with those functions, but with simple functions, we really need to be able to visualize what this vector field might look like. And do a little bit of exploring without having to punch everything into a calculator or type it into a computer algebra system. In which case, the computer algebra system especially would give us the result without any insight at all. And if we didn't bother to think about it, which would be the temptation once we see it, oh, boy, pretty picture. We don't understand that picture, and we might skip the whole process of understanding it, and then we would miss something important. We'd be dealing with something we didn't understand very well. Picture is not understanding, although it can be very helpful. Okay, well, again, if t equals pi over 4, that puts us at this point on the curve, and x is square root of 2 over 2, y is square root of 2 over 2. So that x squared is 1/2, and so also is xy. So that the vector here is going to have component 1/2 and 1/2. So it's going to be directly away from the origin at this point, and it's going to be not quite as long as this one. The magnitude of this vector is going to be about 70% the magnitude of this one. And you should know how to figure that out, and you should understand these numbers well enough that you don't have to write anything down or punch anything into a calculator to see that. Okay, this vector is 70% as long as this one. This is 1/2, 1/2. Okay, this is 1, 0. We can go around to the 3 pi over 4 position. And the only difference here is going to be that the x value is going to be negative. So x is going to be negative square root of 2 over 2. X squared is still going to be 1/2, so the vector is still going to have a component 1/2 in this direction. The y component is still going to be square root of 2 over 2, but the x component is going to be square root of 2 over, the y value is going to be square root of 2 over 2. The x value, the y value is going to be square root of 2 over 2. The x value is going to be negative square root of 2 over 2, giving you a negative j component that has the same magnitude as the j component over here. So your vector is going to be this way. And will in fact be pointing toward the origin. Okay, well, we can take our insights and move them around to the 5 pi over 3 point where the x is still negative, but the y is also negative, so that the xy will be positive now. And to the 7 pi over 4 position. And we can reason that out, and we can reason out symmetries. And we might also consider the t equals pi over 6 value and get some results for that value and for some others. Okay, well, we can do that. We can look at these patterns. And I'm done waving my hand over the patterns, but you can wave your hand and see how all these patterns emerge. Now at this point, it hadn't occurred to me that all these vectors might be radial. It actually occurred that they might, but I didn't believe they were going to because I hadn't done any real analysis. Hadn't really bothered to understand my function the way I asked you to understand this one, so do like I say, not like I did. I ask you to find what happens at the t equals pi over 6 point. What's the f of xy? And also, what's the unit tangent vector at that point? Well, those are very straightforward calculations. You know how to do those. If t equals pi over 6, then x equals the cosine of pi over 6, which is square root of 3 over 2. Y is the sine of pi over 6, which is 1/2. So x is square root of 3 over 2, y is 1/2. Square root of 3 over 2, if you want a number, is about 0.87. You should know that. You should have used that so many times by now that you couldn't forget it if you wanted to. Okay, then we plug these coordinates, the x and y, into our function f of xy, and I'm not going to tell you how it turns out. There's our x, there's our y. Plug them in here. You get 3/4 I plus the square root of 3 over 4j. That's our f value. That's our vector at the point where t equals pi over 6 on this unit circle. So that's like here. at angle pi over 6. We come out, we get to this point, square root of 3 over 2, 1/2. And our value of f is this, which turns out to be 0.75i plus 0.22j. And I'm not even sure I believe those numbers. I believe these numbers. The square root of 3 over 4 is a lot more than 0.22, so how did I... Okay, it should be double that. It should be 0.44. I'll just write over that. We never used that 0.22, and it's a good thing, but at that point I was getting kind of confident. Maybe it was wishful thinking, confirmation bias, or whatever, that this wasn't going to be parallel to the radial line. Turns out it is. Okay, what's our unit tangent vector at this point? Now, right here I've drawn a unit tangent vector. We understand the unit tangent vector. Again, you're being tested over things that involve the unit tangent vector pretty much right now. So what's our unit tangent vector? Well, we just take the derivative of r of t and divide by the magnitude of that derivative. The derivative, well, it's cosine t. X is cosine t, y is sine t. Derivative of x is negative sine t. Derivative of y is cosine t. So that our unit tangent vector is going to be cosine of pi over 6, negative sine of pi over 6 I plus cosine of pi over 6j, which is this. Again, I didn't write down that calculation. You know how to do that calculation. Okay, well, down here I kind of enlarged things now. Here's our point, square root of 3 over 2, 1/2. Here's our f, approximately 0.75i plus, corrected, 0.44j, or 3/4 I plus the square root of 3 over 4j. The vectors kind of look like this. It looks like they might be perpendicular. I still didn't believe they were. Again, I wasn't thinking very hard. At least about that. I was thinking hard about how to explain things. Not sure that had any effect. So, here's our f vector, which is approximately 0.75i plus 0.44j, not 0.22j. And here's our unit tangent vector, negative 0.5i plus 0.87j. Ask people, okay, what would you estimate the dot product of f dot t to be? Okay, and after a while somebody finally said 0. Yeah, that's a right angle. Then you should automatically understand that the closer your angle is to right angle, the closer your dot product is to 0. Now, we want to do a dot product of f with a small vector of magnitude delta s in the direction of the unit tangent. Okay, well, delta s without the arrow is the magnitude of the vector delta s. The vector delta s is going to be this vector delta s in the direction of the unit tangent vector, but a small vector. Okay, a small, corresponding to a small displacement along this curve. So the magnitude of delta s, I say, is equal to this. Now, it might be hard to see what this is. Two dotted lines with a little tiny double arrow between them, indicating delta s is a small number. Okay, so delta s is a small vector, corresponding to a small displacement in the direction of the unit tangent vector, so that that displacement is on or very close to the curve. So we have a delta s increment in the direction of delta t, and delta s is just going to equal the magnitude of delta s times the unit tangent vector, whatever delta s happens to be. It should be obvious why that is so. So what is f dot delta s? Well, we calculate it up here. And I'm going to rewrite a couple of things up here because they don't look very good. You know, the delta s is kind of jumbled in there. So I'm going to just break for a second and come right back.